Welcome to the Spectroscopy and Coherence Scattering Instrument, SCS of the European X-FEL. Here we look at complex materials for technological devices and investigate their structure and functional properties on length scales that are 10,000 to 100,000 times smaller than the width of a human hair. Some of the materials exist in nature, but most of them are actually fabricated down to the atomic lattice in engineering labs. They show phenomena like magnetism, ferroelectricity, or high temperature superconductivity. These phenomena are generated by the interplay of electrons with the atomic lattice. Each electron carries a charge and a spin, and as it moves around the lattice, it also gains an orbital degree of freedom, and it's the interplay of these properties that gives rise to a rich variety of phenomena in these materials. When we look at the electronic structure of materials, we want to learn how we can manipulate them to form new states of matter, or to make them useful in modern technology by increasing, for instance, the energy efficiency as one example, or to use them for information processing and storage. Shining ultra-short light pulses onto the samples, users that come to the SCS instrument can turn insulators into metals or flip the magnetization in the sample on ultra-fast timescales. The processes happen on the femtosecond timescales here. That is a millionth of a billionth of a second. What we have to do to see the ultra-fast processes in our materials, we have to send ultra-short X-ray flashes onto the sample and take snapshots of scattered light to see the details of the electronic structure, like you would do under a microscope. With our fast detector, we can record thousands of frames per second, looking at different time delays of the process. These frames will be put together to form a movie of the process, and there we can see then how the electron dynamics evolves in time. The materials are composed of different atomic elements. When we use different colors of the X-rays, we can distinguish them and see the individual dynamic interplay. In this way, we can see the inner workings of the materials and we can learn how they function. This may help to design better materials for the future.